So this is the review for Unit 5. According to the DuPont Global Automotive Color Popularity Report, 23% of all cars manufactured in the current years. So that sounds like a parameter because it's describing the population. All cars, not just a sample here. So that's definitely a parameter. So right away we think, okay, 23% is a parameter, 23% is a parameter. That's definitely not true. These are definitely not true. 23% is a population. It's a parameter that describes a population here. So we know already it's one of those two. A random sample of cars parked in long-term parking at Philadelphia Airport reveals that 19% of those cars were white. So that looks like a sample was taking. So that would be statistic. So 19% is the statistic. It's got to be B. So 2, a CBS News opinion poll asked 1,190 adults whether they would prefer balancing the federal budget over cutting taxes, and 59% of them said yes. Suppose that, in fact, 62% of all adults favored balancing the budget over cutting taxes. If you select a large number of simple random samples of size 1,190, the sample proportions who favor balancing the budget will vary. Some will be less than 62% and some will be greater, but the average of the sample portions will be very close to 60%. That fact is called what? So low variability is nice. I mean, that means that the values won't vary very much from the 62%. But that's certainly, I don't think that's what it's talking about. Large bias is bad. Small bias vary is not talking about what we're talking about here. It's definitely low bias. So low bias means if you have an unbiased estimator, right? The mean of the sampling distribution will be the same as the mean of the population distribution. So that's what low bias accomplishes, is that those two guys will match. The density curve shows the models below probability distribution of a continuous random variable that is equally likely to take on any value. That's called a uniform distribution there. What is the probability of randomly selecting a value between 0.5, that's right here, 0.5, and 1.2, somewhere about here, 1.2. So that's the shaded area there, just that little sliver. So it looks like the distance there is 0.7 times 0.5, which I believe would be 0.35. So would be the area. Let's see it. So 0.35, there it is. Yeah, I was looking at the wrong answer. Like, where is it? It's got to be there. According to the Humane Society, 39% of households in the United States have at least one dog. In the United Kingdom, 23% have at least one dog. Suppose you select a simple random sample of 75 households in the US and a simple random sample of 80 households in the UK and calculate p-hat, the proportion of households in the US sample that have a dog, and p-hat 2, the proportion of samples in the UK that have a dog. Which I find best describes the mean, variability, and shape of the sampling distribution of p-hat 1 minus p-hat 2. So let's do the easy part first. So we have 39, so 0.39 minus 0.23. Let's make sure that was the order, p-hat 1 minus p-hat 2. So we should get 0.16. So we know the mean is definitely one of those guys. I think B and D are gone. So standard deviation. So what do we do with standard deviation? Kind of remember. So I think we're given. Hopefully, we're given the standard deviation, and we weren't actually. So it's the formula. So standard deviation of the difference is you're going to take the square root of. You're adding this plus this. So it's like p. So 0.39 times 1 minus p, or 0.61, divided by. I think that was 75. Was the end? And then 0.23 times 0.77 divided by, in this case, 80. So I think we'll take that in the calculator. Let's hopefully this works. Square root. Control divide 0.39 times 61 over 75 plus Control divide 0.23 times 0.77 over 80. And let's see what we get. So we get standard deviation is 0.073. There we go, 0.073. I think we got it. That's it. And just to mention, so approximately normal, so you would, to check if it's approximately normal, you would do the large counts condition. So you do n times p, so 75 times 0.39, and then 75 times 0.61, and then 80 times 0.23, and then 80 times 0.77. And you make sure that all of those are greater than or equal to 10. And if they are, then it would be approximately normal, and I think they are. I mean, that's got to be the answer. So, over the past 5 years, it rained 28.3% of the days in Janice's hometown, and it rained on 20% of the days in Linda's hometown. Select a simple random sample of 60 days from the past 5 years for each woman's hometown. Which of the following expressions represents the standard deviation of the distribution of the true difference in the proportion? So even though it's different, we're going to add these numbers. It looks like, it's going to look like this, one of these guys, I believe. So what's the difference between those? The first one was 0.28, 28.283. Genesis and 20% in the other one. So I guess it's over the, let's see. They're both for 60 days, it looks like. So I like the denominator there. I like that denominator for all four of those. But this one just not the right number. I don't love, this should be 0.283 there. But that's got to be the answer. I don't know why they left off the 3. Doctor claims that women that are less than 5 feet tall tend to live to at least 100 years old. Well, I don't know. That plot below shows the result of an average lifespan of 150 simple random samples of size n equals 10. So that's a sampling distribution there. Women that are under 5 foot tall, selected from the records of government issued death certificates. Is there convincing evidence that the mean lifespan of women less than 5 feet tall is at least 100? Just look at the dot plot. The mean is definitely not 100. So let's see. So I'm leaning towards no right away, just because the mean looks to be, I don't know, somewhere in the 90-ish neighborhood. So well, actually, how many are over 100? So let's see. Looks like 1, 2, 3, 4, 5, 6. So that's each tick mark is 2. So that's 98. That's 100 right there, I think. So 1, 2, 3, 4, 5, 6. It looks like there are 6 out of 150 simple random samples. So 6 out of 150. Just for fun, let's just get that percentage. I have an idea, but 6 divided by 150 is 0.04. So less than 5%. So so is there convincing evidence? Oh, the question was not, is the mean 100? Is there convincing evidence that it's at least 100? 100 is, well, we got to think about this. So this is weird because usually we're used to saying when there's 6 out of 150, that's pretty unusual. So it must be convincing evidence. But in this case, only 4% of all those under 5 feet tall lived to be over 100 years old. So I don't think we have enough evidence, right? We need to see more folks who live over 100 in this case. So I know you're used to saying less than 5% is always convincing evidence, but we don't have convincing evidence they're living more than 100. In fact, it seems like, more like in the 90-ish neighborhood is where the mean would be there. So definitely not 100 or more. So I think it's C. That's tricky. You got those sometimes. Suppose you select a simple random sample of size 25 from a population with a mean of 120, standard deviation of 15. Your sample has a mean of 115 and a standard deviation of 13.8. So just one sample has that. Which of the following has a mean of 120 and a standard deviation of 3? So So the random sample of 25 from the population with a mean of 120. So the population has, I guess it's saying, if I read that right, a mean of 120 and standard deviation of 15. So 135, 150, 165. That's the mean. And minus 15, so 105, 90, and 75, I think. Okay, I got to think about this. So this is a sample, a random sample size 25 from a population. So this is the population here. So when you take samples of size 25, it's going to have a smaller standard deviation. So you've got the new standard deviation will be 15 divided by the square root of n, which is 25, which ends up being divided by 5. So you get 3 there. That's it, isn't it? So that's where that comes from. That's this sampling distribution of the sample mean, I believe. If you get a bunch of sample means, if you do the sampling distribution, I believe that would be C. Boy, you got to be careful of the wording here. That's a sneaky one. In order to use the formula that to calculate the standard deviation of the sampling distribution, so before you can use that formula for sample proportions, what do you have to check for before you do standard deviation? So that's the standard deviation formula. So I think it's the less than 10% condition. So I know 3 is true. Population is approximately normal. It has nothing to do with standard deviation. NP greater or equal to 10, that has to do with normality. So I think it's only C. So it didn't say you have to prove both normal and use standard deviation, just can you use a standard deviation formula? I think that would be 8 is C. Which of the following is an accurate restatement of the central limit theorem? Ooh, okay. I like the way this one starts. For sufficiently large samples of size n from a population with standard deviation that, regardless of the shape of the population distribution. That seems right. Let me see. For sufficiently large from a normally distributed. So it doesn't have to be from a normally distributed population. So I don't think that's right. Large sample from any population, the sample distribution is approximately normal regardless of the shape. We got to think about what's the difference between A and C. I'm going to have to think about that. Okay, so what's sneaky about A is true, but it's not really the central limit theorem. So I think this is the central, sufficiently large, even if you know, it doesn't matter the shape of the population, the sample distribution of the means is approximately normal. So I think that's the central limit theorem. So even though A is true, these just don't even hold water. They're not the central limit theorem. It doesn't sound like it at all. So it's got to be C. Dogs vary in size more than cats do. Suppose the weight of a dog asserts that he has a mean of 28, standard deviation 14. Cats, mean of 9.5, standard deviation 2. Cats' weights are roughly normally distributed, but dogs' weight are skewed to the right. Suppose you select a random sample of 10 dogs and 8 cats. Which of the following is accurate description of the center, variability, and shape of the sample distribution of the sample mean weight of dogs and the mean weight of cats? Okay. Okay, so let's do the 28 for mean of dogs minus 9.5. It's 18.5. Oh, well, pretty much all of them are 18.5. That doesn't help us that much. Standard deviation, when you subtract, let's see, you got to do the square root, control divide. So I think it would be the, this is for means. Ooh, okay, this is the means one. I think this is the formula. I think it's 14 squared. I hope this is right, 14 squared over the size, which is 10, that's n, plus, I think this one is 2 squared, standard deviation squared, over 8, I get 4.48, so I'm leaning towards either A or B there. Approximately normal, I don't think so, right? Because you saw how small these were, and only one of them was actually normally distributed. That would have been okay, but the other one wasn't. So central limit theorem doesn't apply, so that's not true. So it's got to be B. But I didn't read E. Standard deviation cannot be determined. Yeah, we can determine standard deviation. That's not it. Okay. Study of college freshmen study habits found that in the time, in hours, that freshmen study each week follows a distribution with a mean of 7.2 hours and a standard deviation of 5.3. Can you calculate the probability that randomly chosen freshman studies more than 9 hours? So, so we don't have to do any calculations here. This is not a sampling distribution here of a certain sample size. Like this is just saying, hey, let's just take the mean of 7.2. 7.2, that's 0.2. Standard deviation of 5.3. And it says more than 9. So somewhere over here is 9. We're shading to the right. So we would just do, I think we just go maybe 652. Norm CDF, this guy. The lower bound is 9. The upper bound is infinity. I'm just going to type 999. The mean is 7.2. We don't have to adjust those because it's not a sampling distribution. We didn't take a sample of a certain size. If you want to think about sample size as 1, that would be bad. You could divide by square root of 1 there. So we should get point, and we would write the command here. So norm CDF 9 comma infinity comma 7.2 comma 5.3 equals 0.367, and that's the lower upper mean. Sorry, this is really sloppy, but you get the idea. We'll label those inputs for the calculate command every time. What is the shape of the sampling distribution of the mean weekly study time for samples of 55 randomly selected freshmen? What is the shape? So 55 randomly selected freshmen. So that's is this means or proportions? This is means. So 55. So because of the central limit theorem, because 55 is greater than or equal to 30, that's going to be approximately normal. Approximately normal. Calculate the mean or standard deviation of the sampling distribution of the mean weekly study time for X for samples of 55 randomly selected freshmen. Calculate the mean and standard deviation. So the mean of the sampling distribution would be the same as the mean of that, so 7.2. That's the mean. Then the standard deviation of, I guess this would be X bar, would be the standard deviation of the population, which is 5.3, divided by the square root of n, which is 55. So 5.3 divided by square root of 55. 0.715. Find the probability that the mean number of hours spent studying by an SRS sample of 55 students is greater than 9. So using these two, so very common on this kind of question, we're going to use the two that are given to us. We know the mean is 7.2. We know the standard deviation of this guy for X bar is 0.715. And what more than 9? So 9 is like right here. So it should be a little different than the first time because we have a different standard deviation. So I'm just going to copy and paste this and change the standard deviation to 0.715. I think that should be right. So again, we write down the full command there, norm CDF 9 comma infinity comma 7.2 comma 0.715 equals 0.0059. Oops, 9. And then label those lower, upper, mean, and deviation. Okay, two slight fixes, I believe. So I definitely should have checked the less than 10%. So we think that, what's that number? That 55 is less than 10% of, and what would you say in words? This is, so, right, it's like, so 10% of all the freshmen at this school, and we're going to assume that's true. And this one, I don't think that's right, actually. It was going to be right, but the problem is it's a sample size of one, so it doesn't, central limit theorem doesn't apply. And unfortunately, they didn't tell us the shape of the population. So I actually think this one we shouldn't have done. We should have, and well, I mean, that might be the case. If the population is normal, yeah, but we don't really know the population is normal, and central limit theorem can't really help us out because we're taking sample of size one there. It's not really a sampling distribution per se, so it's not going to work. Athletic participation. Suppose that 20% of students at high school A and 18% at high school B participate on a school athletics team. Okay, to put independent random samples of 30 students from each school are selected, and they're asked if they participate on a school athletic team. Let P hat A represent the sample population of students at high school A who participate on an athletic school team, and let P hat B represent the sample portion at high school B who participate in an athletic school team. Is the shape approximately normal? Justify your answer. Okay, so these are percentages. So for it to be approximately normal, you have to check the large counts condition. So 30 times 0.18, and then 30 times 0.82. Well, let me just do 30 times 0.18. I'm not real optimistic about this. About 6 almost, 5 or 6. This doesn't pass the large, that's not greater or equal to 10. So it is not approximately normal because it doesn't pass the large counts condition. Calculate and interpret the mean of the sampling distribution. So means are like normal here, so we would just do the mean of P hat A minus P hat B, so 0.18, oh sorry, 0.20 minus 0.18, so 0.2 minus 0.18 is 0.02. So it's not bad to show that work here. I like to put the unit here. So this is 0.02 percent. So those are, this is the amount. I just want to think about what it is. So folks that play on an athletic team. So interpret the mean. So if we took every possible sample of size 30 from both populations, both high schools of students who, and found the proportion of students who play an athletic sport, then the average difference of the population mean would be 0.02. Something like that, I think, would work. Verify both types of independence in the setting. So then calculate and interpret the standard deviation. So we want to do the test. This is percentages. So the less than 10% condition. So 30 is less than 10%. This should prove independence of all students at high school A. That's fair. And then you repeat it of all students at high school B. Right? You're just saying the same thing over again. Then calculate and interpret the standard deviation. So the standard deviation is going to be the square root of PQ, so 0.2 times 0.8 over 30, I believe, plus 0.18 times 0.82 all over 30. So let's type that in. Square root of 0.2 times 0.8 all over 30 plus 0.18 times 0.82 all over 30 is 0.101. So interpret that. So if we took every possible sample of size 30 from high school A and every possible sample size 30 from high school B, found the proportion of students who play athletics, then the typical variation from the difference in population standard deviations, I'm missing it, is 0.1. Wording there is typical difference in population proportions. It would be 0.101. 13, at a small school, there are only 5 students taking AP Calculus BC. Table below provides some information about these students as SAT scores. List all 10 possible super random samples of size n equals 3. So you could put, I'm just going to be very systematic, 740, 700, 800 together. You could put 740, 700, and 740 together. 740, 700, and 780. Put those together. I think those are all the ones that start with 740, 700. Okay, let's get all the 740s. And then the next number is 800s, comma 740. And then the 740, comma 800, comma 780. And then the 740, 740, 780. Got all the ones that start with 740. Now let's get the ones that start with 700. So 700, comma 800, 800, comma 740, and 700, comma 800, comma 780, and then 700, comma 740, 780. I'm trying to be very systematic. And then we got all the 700s, and then we have one more 800. Hopefully I got this right. Comma 740, comma 780. Okay, so then we're to get the, let's see, we're finding in this case, sometimes they ask about range or means. In this case, it's the median. So what is the median of those numbers? So in the middle would be this one, if you put them in order. 740 is the middle. 740 is the middle. A lot of 740s. 740 is the middle, I believe. 780 is the middle here. 740 is the middle here. 740 is the middle here. 780 is the middle here. 740, I think. 780, I believe. So a lot of 740s. I think there's 3 780s and 7 740s. So then you're supposed to put it on a dot plot. Just look at this one. They did this for us, 13A. So we did that right, I think. Here's the dot plot. So you've got the dot plot here. You can see there's 7, and they title it. That was very nice. 7 740s and 1 780. They just plotted on a dot plot. Sample median SAT scores. Is a sample mean an unbiased estimator? So then you would need to find the mean of all those. So I think it was 7 times 740 plus 3 times 780. That's the total of all those added together. Divide that by 10. I get 752. If I find the median of these guys, let's see, the lowest is this one, the biggest is that one. Those two, so it's 740. So 740 doesn't match 752, so it's a biased estimator. Median is not, in this case, because the sample distribution of the means of the sample median is not equal to the population median. That's a biased estimator, so it's no good. Last question. The age at which smaller breed of dogs are fully housebroken vary from a normal distribution of mean of 6 months. Wow, it takes a while. Standard deviation of 2.5, the age at which a large breed of dogs are fully housebroken is 4 months with standard deviation of 1.5. So, okay, they're faster. Suppose we select an independent random sample of 25 small breed dogs and 25 large breed dogs. The difference, it'd be the difference small minus large. What is the shape of the sampling distribution of XY? So of the difference, so the shape. So what test does it have to pass here? So it doesn't pass the CLT here, so that's not good. So, but it does say normal distribution for that guy, normal distribution for this one, because you would say something like because both populations come from normal distribution, the difference will also be a normal distribution. Find the mean of the sampling distribution. Well, that's just, type it in your calculator. So that would be the small one was, so it was mean was 6 minus 4 of the large one, which is 2. So 2 months, and it's not a bad idea to put 6 minus 4 equals 2. It's good to show you work, 2 months there. Verify the 10% condition is met. So we should check the 10% condition. So 25 is less than 10% of all small breed dogs it doesn't say from where, but everywhere, I guess. And then you repeat that 25 is less than 10% for all large breed dogs. And then calculate the standard deviation. So the standard deviation, this is means. So we want standard deviation, so it's square root of standard deviation squared, so 2.5 squared over 25 plus 1.5 squared over 25. I think we should do that in our calculator. It should work out. So square root of 2.5 squared over 2.5, no, 25, sorry, got confused, plus 1.5 squared, I believe was the other one, over, I think that one was also 25. So we get 0.58. We don't have to interpret it, 0.583, I guess. Should we be surprised if the sample mean housebroken age for small breed dogs is at least 3 months more than the sample? So let's kind of draw this. So the differences, so the difference was 2, standard deviation was 0.583. So we want to have is at least 3 months more. So the sample breed for small is 3 months more. So small minus large, so that'd be 3. So I think it's 3, right? So if this was positive 3 or more, so at least 3, so something like that. I think that looks right to me. So I think we'd go norm CDF this guy. So menu 652, lower bound 3, upper bound infinity, mean of 2, standard deviation of 0.583, and you get you'd show the work norm CDF and you'd write the answer 0.043, I believe. Let's see if we got that one right. 0.043. Yeah, 0.043. Sounds good. Yeah. Okay, I think that's your review. Again, if you want to look over the answers there in case I missed something, not a bad idea to do that.